Hello and welcome to Lars's Electric Endeavors. In this video we will set up a project for this Nucleo board using this kit, the Freedom Kit. And this is a method for setting up a project for developing software for these chips in such a way that we don't have to use the CubeIDE as our integrated development environment. We can use any IDE when we have this kit. And we're going to be using Cursor, and we will be experimenting with AI to generate C code for these targets in future videos. This kit also provides us with a way where we can use the CubeMX tool to generate our boilerplate initialization code, as you saw in the previous video perhaps. This tool is very powerful for getting started and for configuring all the registers and features on the chip in a graphical way, and the tool will generate like a platform to build the software on. And the problem is they want you to use their platform the way that their code structure was made, and yet they want you to insert your code into that. But I don't like that particular structure very much, so what we will be doing here is we will be making our own code structure, where we have a hardware abstraction layer and we have a driver layer perhaps, and an application layer. And inside that nice and neat structure, we will simply include the CubeMX as a library, as something external. So we don't have to look at that. It will make sense in a few minutes when we configure this project according to this method. So why don't we get started here? So the installation of prerequisites. We already installed the CubeMX in the previous video, and we installed the kubeclt tool. And what we need to do now is to make the tool chain to install that. And here we are simply doing apt installs. And build essential, I'm really messing this up. Build essential is a packet that will provide us with make and cmake and all sorts of other binaries that are often necessary to build projects in Linux. And we need that for this tool. Also, here you have a suggestion to install the cross-compiling ARM toolchain. We're not going to do that because when we install the kubeclt, here I'm tab completing, we already got the ARM toolchain installed. And this one is, let me see here. It's already a totally fine version suitable for our task. But if you didn't want to have this tool installed, you could totally get access to this toolchain by simply running this apt install. So now it's time to install Cursor. And how would you do that in Linux? You would simply search for Cursor and then go on the website and click the download. And there is a deb file coming our way. But I already downloaded this deb file, and I just want to show you what happens here. I double click the deb file. This is a downloadable, basically apt packet that you download. So instead of using the apt install here, we are basically downloading the deb packet. But you see that there is actually a problem here. It did not work by simply double clicking this file. And this is just one of many problems that you might encounter in Linux. Sometimes things are not super polished. And if you are a beginner, I totally understand why this might be super frustrating. And that's why I wanted to show you how you might run into an issue here. And what I do then when stuff like that happens, I open a terminal instead. You see here we are in this folder. And then I'm going to do the task using the command line instead here. And to install a deb file, we need to use something called dpkg. And we need to run it as sudo as a super user. And that will install the deb packet. And when you run it from the terminal, at least sometimes you can see a more descriptive error message if something goes wrong. But in this case, we are now presented with this dialog here, and we can say yes to that. And you will see that it works now. And now I believe we have cursor. There it is. Yeah, so that's the installation of cursor. Yes, I'm going to do the login now, and I will just pause the video. So there you go. I managed to log in with cursor, and I believe we can close some of these tabs. And now here we have cursor ready to use. And I want to put this at the left and the guide at the right here, because now we're going to follow the guide. And now we can do this conveniently here. So yeah, actually the first step is to make the project in CubeMX. Let's do that. We did the same in the previous video. Let's do it again here in this video. We have to create a new project using the board selector here, you see. And this wallet. I'm not sure why it needs this wallet. The board selector. And we will pick this particular board. And here you can see there are some exact steps that are necessary for the Freedom Kit to work as intended. Here we have the board 401RE. And I double click it. And here we have to say yes to that. And here we have this brilliant visual overview of the controller. And like last time, we're just going to leave everything to default. And we go to the project manager, and then we have to pick the name CubeMX. Here. And we have to specify the project root. And for the project root, we need to make an empty folder. Why don't we just do that here in cursor here? So I will say development. I'll make an empty folder for this project here. I'll call it Freedom, because we're using the Freedom Kit. And now here I will specify this folder as the project location here. We pick advanced, we do not generate main, and we pick CMake here. Advanced, CMake, save project and project folder. So I believe by saving the project, yeah, in cursor we have the agent view here. I don't like that very much. I prefer the editor view. And let's get rid of the chat for now. So cursor saved the project now in the IOC file, and here we can actually take a little peek inside the CubeMX project, and it's good to keep this file here. And it's time to generate the code. Okay. So now in CubeMX we have all the generated stuff from from the code generation here, and this is the structure I was talking about in the introduction. And you see how we have all these super ugly comments where that you're supposed to put code in particular places here, and you're supposed to look at all this stuff here. Normally I would hide all these things in the hardware abstraction layer, or I don't want to look at this in our main code structure. Now we copy all the files from the project root of this repository. So we need to clone it here, and I will just copy like that. I will go to the temp folder here. So there you have the to project root. There it is. And I will show you another little gotcha that might happen here. So if you notice the files in the project root, there are like 1, 2, 3, 4, 5, 6, but we only see 4. The reason is that the files starting with a dot, they are hidden in Linux. This is the way to normally hide files in a very superficial way, but still the files are hidden by default. And we need to deal with all of them, not only the visible files. And what to do here is to simply push Control H in the file manager, and that will toggle showing hidden files. And now we definitely want to include them, and we will Control A for selecting all the files, and Control C for copy. And paste is not working. Sometimes, again, this inconvenience in Linux, not all features are working as smoothly, but we can use the cpaste instead. Cpaste is part of the clipboard files project. Here's the help for that, in case you're curious. The clipboard files provides us with terminal commands where we can interact with the files on the desktop environment clipboard. So using the cpaste command here, I was able to paste the files that we copied into the root here as we're supposed to. That was this step. Now we go into the CMake list. This is the configuration file for CMake, and CMake is the build tool we are using here to configuring the build. And we can pick another project name here. I'll just call it Freedom. And save. Control S. Build sh. That's the build script provided by the Freedom Kit. And here we also have to set the name. Yes. Adjust variables in post cubemx gen sh. This script is the magic regarding CubeMX, because this script will copy the files generated by CubeMX into another folder where it will be suitable for including in our main code tree, as I talked about in the beginning. But we have to fix a few things here. And you can see that there is a startup file. I wonder if, let's see here. I'm a little bit wary with letting cursor do this for us. Let's just take a look. That looks okay. This one is not okay. I will just put in the right name here. And the family here, this variable is used down here. And oops. Let's just check exactly what is the file name that we have to match here. So it's in the core folder, CubeMX folder, core, source. So that is the correct prefix. Whoops. And it's not correct. This is a good example of how sometimes when you use the tab complete, you end up spending more time. If I just did it the right way the first time, this would have been correct from the beginning. So that was the fixmes inside of this file. And now we can run this script. Let's go back to the root. Here you can see we have the script ready to run. And as you probably know, you need to use the // to identify a file in the same folder. And it was not the right name. Let's take the right name, put it here. Try again. Okay, and the script ran to completion. And it generated the folder here where we have the CubeMX code transformed slightly so it can be included from our main source tree. Let's talk about this source tree. So here we have the main.c. And this is where we have the main function. And there we initialize our hardware abstraction layer. And then we run our main application here with the start function. And the hardware abstraction layer is this H file where we initialize things related to the hardware. And then at this point, we have only 3 functions available here. We can make a sleep. We can set the status of the LED. And we can read the status of the button if it's pushed or not. And inside the hull, there's another fix me, by the way. Here we are actually invoking the CubeMX generated initialization. And here we are invoking functions from the cube generated code. But the entire point is that we have it nicely wrapped in a structure that we can handle here. Also, we have a module for handling the serial port. So let me talk about the test environment. So the script provides us with a structure to run interactive tests on the serial port provided by the USB. And these tests allow us to interact with the hardware step by step and verify if the features work as intended. And right now we have 3 test functions provided as an example here in this kit. And these functions, for example, look at this hello world. There is a printf with some text. And then there's a loop where we are receiving characters from the serial port. And we are reacting to the characters. And then in the end we return the result of the test. And this particular test is not it can pass or it can fail according to what you click, and it can also return something called neutral. Here we have another test case where we are investigating the LED if it's blinking as expected. It should blink with 1 Hertz, 1 time a second. And if you actually see it blinking with that frequency, it tells us that this function is correct, at least approximately. And it also tells us that the HAL LED control function works. So this test case will test those 2 functions. I think that was enough blabbering. Let's just build this and see what happens. This command will build the main application. Yeah, and it's time to fix the last fix me's here. Come on, Cube, help me. I'm gonna be brave here and see if Cube got it right this time. Sorry, cursor. It did. We managed to program. So we managed to compile it. And now we will plug in the programmer. And we can run the command that will program the target. And it worked. We have a blinking LED. And when I push here, it blinks faster. So that was the first part of the demonstration here. The second part, I will build the interactive test suite, and I will show you what I was talking about here, how it looks like to run these 3 test cases. To do that, we have to write test instead of app. Let's just take release again. and we built the test suite and we programmed it. And to do anything, we now need to interact with the serial port. And for that purpose, we need a program that we can, it's called a terminal program. And I like to use PuTTY for this. And then we need to open the serial port, and we will be presented with the interactive test suite. So it's serial. So what device to enter here? In Linux, let's make a new tab here. I like to run the dmesg command because it will give us clues about what happened when we inserted the USB. The kernel in Linux handles the hardware, and it will give us some messages about what happened. And here you can see that we got a TTY ACM0. These are all our TTYs, and here you have it. This is the one we need to use here. And the speed, let's just do it the right way. So let's look at the configuration of our controller, because we will be talking to the chip now. And if we look here, connectivity, UART, you can see that we are going to be using 115/200 baud, which is a very standard baud rate. Let's just save this as a session here. Okay, I have some garbage here. Let's try to restart it. There you go. There you have our interactive test suite. And here you have the first test case. Observe LED blinking with a frequency of 1 Hz. And now I could take a stopwatch and I could actually measure this a bit more accurately. But I will just continue this test case here. And here we have the hello world. I pushed 0 and I got a hello message. That's nice. Let's just, for fun, let's just try to fail this one. You see we got a fail here. And then there is another example in the kit provided, which is the assert demo here, where we are asserting some simple stuff here. This one passes. And in the end we have a pass, we have a fail, we have a neutral one. And we can restart the test. And this pass it this time. So now we have 2 passes and a neutral. Isn't that great? Now you saw an example of how we can set up a project for the STM. We can build it, we can compile it, we can program the code into the chip without using the CubeIDE, but we are using scripts inside our favorite IDE for that task. I feel like we should just try one thing now. Why don't we try to ask the agent, or the chat at least, to write a new test case for us for testing the push button? Because as you saw, there is no test case to verify that the button works. And the test cases there. Inspiration. Add a test that verifies the button. Hell get button is the relevant function. Let's see if that works. It looks pretty promising. It's reading all the code. I feel like we have a benefit now by having a clean software structure. and not the confusing structure generated by CubeMX. Hell button, very nice. I feel like the AI is better off looking at a clean structure like this than if it had to look through all this mess. It's doing stuff. Now would have been a good time to go and grab some coffee or something. And it made a little essay for us. I'm just gonna keep all. I'm just gonna feel lucky here. Let's build the test. It did not work. It's because we have a variable that is not being used. Okay, dear cursor. Run. The build like this. Oh, whoops. And fix the error. Let's see if that works. Okay, you're allowed to do it now. So actually the agent ran the script that programmed the device and started the test case. So let's see now. We have the blinking LED. Test hell button. Testing the hell get button. Release, press, release. Okay, and it verified that the button worked. Brilliant. So I feel like the AI made something that worked for us. Maybe it was a little bit more verbose than I would have made it. I would have written this function in half the code. Anyways, it worked, and it was just a brief demonstration of how you can use AI for embedded software in a project made by the STM32 Freedom Kit. Let's wrap up the video here. Thanks for watching, and see you in a future video.